When students have mastered adding a two-digit number to another two-digit number, and the multiples within 100 of the digits that make up the base 10 number system, they are ready to construct the meaning of multiplication. Multiplication involves finding the product of two factors, where one factor is repeated a number of times that is determined by the other factor. First, we will consider the meaning of multiplication in numeration, or how many. An array is an arrangement of objects into rows and columns. A multiplication number model can be thought of as representing or represented by an array, and the product is the cardinality of the array, or the total number of objects in the array. By convention, the rows of an array are the first factor, and the columns of the array are the second factor. In this example, we have 3 rows of 6 columns, or 3 rows of 6 counters in each row. This represents the multiplication problem 3 times 6 equals 18. In order to encourage students to think in terms of numeration, we can say 3 rows of 6 make 18, or more generically, 3 groups of 6 make 18. Although multiplication is commutative, that is, the order of the factors does not affect the product, it is important to follow the convention of rows times column so that students will be successful applying multiplication, where it is often important to keep the number of groups distinct from the number of items in each group. We will use the distributive property to construct multiplication by using products that we already know to find products that we do not yet know. Although the distributive property may be confusing in its algebraic expression, it is really very simple. This example shows a 4 by 7 array representing the multiplication problem 4 times 7. We can break this array down into 2 parts. The blue part contains 4 rows of 5 columns, and the red part contains 4 rows of 2 columns. We have broken 4 by 7 down into 4 by 5 plus 2. Now we find the cardinality of each part and then add them back together. The cardinality of the blue part is 4 times 5. The cardinality of the red part is 4 times 2. Thus we have shown that if we do not know what 4 times 7 equals, we can find the product of 4 times 5, the product of 4 times 2, and add them together to get the product of 4 times 7, which is 28. We can visualize arrays in a manner similar to the MathRack number grid, using color coding to show the composition we are interested in at the moment. In this case, 2 red counters and 1 white counter show that we can consider arrays with 3 rows to be an array of 2 rows plus an array of 1 row. If we know all of the products of 2 but do not yet know the products of 3, this will help us to construct the products of 3 from the products of 2. In this example, the red array is 2 groups of 2, and the white array is 1 group of 2. We can combine these 2 subarrays to form an array of 3 rows of 2, and see that the cardinality of that array is 4 plus 2, or 6. Thus, we have shown that 3 times 2 equals 6. At this stage, we are concerned only with the concept of the distributive property and not with any of the formalities. We do, however, want to encourage students to write rows times columns. We start with simple arrays that are easy to visualize and then move on to arrays where students may actually not know the product. Drawing a line to divide the array into 2 parts often helps students to keep the parts distinct in their minds. In this case, we have a 2 by 7 array above the green line and a 1 by 7 array below the green line. When we combine these, we get 3 times 7 equals 21. Even if a student has memorized this product, you can ask them why 3 times 7 equals 21. Of course, many factors can be composed in more than one way. We can think of 6 as being 3 plus 3 or double 3, and we can break an array with 6 rows and 3 columns down into 3 groups of 3, which makes 9, and another 3 groups of 3, which makes 9, to see that 6 groups of 3 make 18, so 6 times 3 equals 18. We can also think of 6 as being composed of 5 and 1. 5 groups of 3 make 15, one group of 3 makes 3, and when we combine these, we see that 6 groups of 3 again make 18. Students who make many overlapping connections to the meaning of multiplication in numeration will have a strong foundation for multiplicative thinking. Multiplication can be distributed over subtraction as well as addition. For example, we could think of 8 as being composed of 5 plus 3, but we can also think of it as being composed of 10 minus 2. 10 groups of 5 make 50, which is easy to compute. So to find the product of 8 and 5, we could subtract 2 groups of 5, or 10, from 50 to obtain a product of 40. Thus we have shown that 8 times 5 equals 40. By now you have probably started to see why multi-digit addition and subtraction is an essential prerequisite for constructing the meaning of multiplication. Students will not be able to use the concept of the distributive property if they are not able to fluently add and subtract two-digit numbers. It is important to remember that at this point we are not concerned with the formalities of multiplication or the distributive property. We want to keep our focus on the concept of distributing the multiplier and the language of numeration. 10 rows of 6 make 60, and 2 groups of 6 make 12, so 8 rows of 6 must make 48. We also want to develop students' understanding of the meaning of multiplication in magnitude, or how much. This is the area interpretation or area model of multiplication. It is conventional to write area as width times length in the same way it is conventional to express arrays as rows times columns. It is important to resist the temptation to refer to width as height, because height is the third dimension needed to construct the volume of a rectangular prism. In this example, the rectangle has a width of 3 units and a length of 6 units. It represents the multiplication problem 3 times 6 equals 18. In the language of magnitude, we would say that the area of a 3 by 6 rectangle is 18 square units. Here we see a rectangle whose width is 4 units and length is 6 units. We can find the area by counting by 6. 6, 12, 18, 24. The area of a 4 by 6 rectangle is 24 square units. Here we see the same rectangle turned on its side. Now the width is 6 and the length is 4. We could count by 4, but in this case it is more efficient to use the commutative property and count by 6s again. 6, 12, 18, 24. The area of a 6 by 4 rectangle is also 24 square units. The area grid is color-coded to emphasize squares. The unit square of 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. Squares are similar to doubles in addition, but they are more mathematically meaningful, in addition to providing landmark numbers for constructing the meaning of multiplication within 100. See if you can detect the pattern in the sequence of squares. One obvious pattern is that the squares alternate odd and even numbers. However, there is a more profound pattern hiding underneath this superficial pattern. Notice the difference in successive squares. The difference between 1 and 4 is 3. between 4 and 9 is 5, 7, 9, 11, 13, 15, 17, 19. This pattern arises from the way successive squares are constructed. Two sides of the previous square must be covered, and an additional unit square must be added on the diagonal to complete the new square. This guarantees that each successive square will add an odd quantity to the previous square. This underlying pattern produces the odd, even, odd, even, odd, even pattern because adding two odd numbers produces an even number, and adding an odd number to an even number produces an odd number. The area interpretation of multiplication leads naturally into the multiplication table, which is also color-coded to emphasize squares. The multiplication table also shows that a multiplier of 0 always produces a product of 0. Neighboring multiples provide an effective way to consolidate and reinforce patterns in the multiplication table. For example, consider the product of 6 and 7. If we know that 5 times 7 equals 35, we can count up by 7 to get a product of 42. Or, if we know that 6 squared is 36, we can count up by 6 to get 42. Constructing the meaning of multiplication is a challenging and time-consuming process for many students, but the benefits are tremendous. Not only will students be fluent with multiplication facts, but they will have a deep understanding of multiplicative thinking that will prepare them for success with division, fractions, and beyond.